This is part 1 of the voiceover lecture for Chapter 13, the gases. I've divided Chapter 13 into 9 sections. In Section 1, we'll discuss kinetic molecular theory. Section 2, pressure. In Section 3, we'll discuss Boyle's law. Section 4, Charles' law. Section 5, the combined gas law. In Section 6, Avogadro's law. In Section 7, the ideal gas law. In Section 8, we'll discuss what happens when you have a mixture of different gases. And in Section 9, we'll discuss gases that are involved in chemical reactions. Section 1, Kinetic Molecular Theory. The kinetic molecular theory of gases helps us to predict the properties of gases, especially under changing conditions. This theory relies on 4 assumptions. First, that the particles, the atoms and molecules of a gas are always in motion, as you can see in the animation to the right. Interestingly, these molecules are slowed down 2 trillion times what their speed would be at room temperature. Second, that there is no attraction or repulsion between the particles. Think of the atoms and molecules of a gas like billiard balls bouncing off of each other when they smack into one another or when they smack into the sides of the container that they're in. Assumption number 3 is that there's lots of space between the particles. You can see again in the animation to the right that there's lots of empty space between each particle. And assumption number 4 is that the speed of the particles increases with increasing temperature. Alternatively, the speed of the molecules would decrease with decreasing temperature. One of the properties of gases that's predicted by this theory is that gases are compressible. You can squeeze them. Because there's an abundance of empty space between the particles of a gas, these particles can be forced closer together. You can see this demonstrated in this picture to the left. We will illustrate many of the properties of gases throughout this chapter using a similar setup. The gases are contained in a hollow cylinder with a movable but airtight piston, just like you'd find in an internal combustion engine. In comparison, liquids are not compressible. You can see in the picture to the right that because liquids lack the large spaces between particles, they are already tightly packed. Therefore, you can't squeeze the particles closer together. Another important property of gases is that they assume the shape and volume of their container. Compare this to liquids, which take on the shape but not the volume of their container. And finally, gases have much lower densities compared to liquids and solids. As you can see in the picture to the left, the particles are very far apart. Recall that the formula for density is the mass divided by the volume. Mass is usually measured in grams and volume in milliliters, so the units for density are usually grams per milliliter. To illustrate the idea of the very low comparable density of gases, imagine a pop can filled with water. Now imagine you take that 1 can of water and then convert it into steam. To maintain the same internal pressure, you would fill 1,700 cans with that steam. Section 2, Pressure. What is pressure? Pressure is the result of the constant collisions between the atoms and molecules in a gas and the surfaces around them. Pressure is calculated as the force divided by the area. In the case of gases, the force is dependent on the density of the gas. Think of it this way: the more molecules that are colliding in a particular area, the stronger the force will be, and therefore the stronger the pressure. Another example to illustrate this is as you go up in elevation on the Earth, like when you climb a mountain, there are fewer air molecules. The density of the air around you is lower. There are less molecules colliding with your body, and you experience this as a decrease in air pressure. Another way to illustrate this is if you have two containers of the same size. In one container, you have fewer molecules, and in another container, you have more molecules. The container that has more molecules crammed into the same volume will have a higher pressure. The density of the gases is higher. There are more molecules colliding with the sides of the container. There's more force on the sides of the container, and therefore the pressure is increased. You should know the following example of how we experience changes in air pressure. You have probably felt this for yourself. When you travel up or down in altitude somewhat quickly, like on an airplane, your ears pop. What causes this popping sensation? First, let's review a bit of biology of the ear. Your ear is made of three major areas: the external ear, the middle ear, and the inner ear, which is not shown in this diagram. The middle ear and external ear are divided by the tympanic membrane or eardrum. When you travel up in altitude, the air pressure around you, outside of your body, decreases. So relatively, the middle ear now has a higher pressure. This puts unequal pressure on the eardrum, pushing it outward. This can be painful and even rupture your eardrum if the pressure isn't equalized. The key to equalizing the pressure is the eustachian tube. Remember, this is a tube that connects the middle ear to the nasal cavity. Normally, the eustachian tube is pinched closed, but when you yawn or stretch the muscles in your jaw a certain way, it opens the eustachian tube. Now air can be released from the middle ear. The release of this air allows the eardrum to recoil back into place. This is the popping sensation you feel. There are several units of measure that are commonly used for pressure. First is the atmosphere, or ATM. As its name suggests, it's the average atmospheric pressure of the Earth at sea level. Next is the Pascal, abbreviated capital P little a. Remember, pressure is calculated by taking the force and dividing it by the area. A Pascal is calculated with units of newtons for force and square meters for areas. So a Pascal is equal to 1 Newton per square meter. Units of pascals are much smaller than ATMs. 1 ATM is equal to 101,325 pascals. Another unit of measure of pressure is the millimeter of mercury. Hg is the chemical symbol for mercury. The term comes from an old style of barometer. A barometer is an instrument used to measure atmospheric pressure. Because of the health dangers of mercury, these barometers are rarely used today. Traditional mercury barometers are fairly simple devices. They consist of a tube and a dish, as can be seen in the diagram to the right. The dish is filled with mercury and is open to the air. The tube is closed at one end and open on the other. The tube is filled with mercury and then inverted, so the open end is submerged in the dish. The mercury in the tube does not completely empty into the dish because the atmosphere exerts a force, air pressure, on the dish of mercury. This pushes the mercury up and into the tube, countering the downward pull of gravity. The height of the mercury in the tube on average is 760 millimeters. Hence the name of the unit, millimeters of mercury. Local changes in air pressure exert varying amounts of force on the dish of mercury. This in turn affects the height of the mercury in the tube. Changes in air pressure can be predictive of weather events. This is why barometers are so useful. Note that 1 atm of pressure is exactly equal to 760 millimeters of mercury. Here's a table of the most common units of pressure. You will have to convert between units of pressure. but you do not need to memorize these units as this table will be provided on the test. The way you read this table is that all of the numerical values as written in the right-hand column are all equal to each other. In other words, 1 atm, for example, is equal to 760 millimeters of mercury. 760 millimeters of mercury is equal to 14.7 psi, and so on. Converting between units of pressure is a simple matter of dimensional analysis. As you learned last semester, first you want to make note of the given values. Then you want to make a solution map. That includes using the proper conversion factors. Then you solve the problem. Let's try an example together. At the top of Mount Everest, the pressure is 0.311 atms. What is the pressure in millimeters of mercury? We are given the value of 0.311 atms, and that's all. Our solution map is thus fairly simple. We need to convert from atms to millimeters of mercury. Using the table from the previous slide, we know that 1 atm is equal to 760 millimeters of mercury. That equality will act as our conversion factor. Here we can see the problem fully written out. Remember that we're canceling units of atms. So atms must be in the denominator in our conversion factor. Again, no atms cancel. You're left with units of millimeters of mercury. The answer rounded to the proper number of sig figs is 236 millimeters of mercury. Section 3. Boyle's Law. Our first gas law up for discussion is Boyle's Law, named after its discoverer, the Irish natural philosopher Robert Boyle. Boyle made his discovery in the 1660s. Boyle was a contemporary of other famous scientists like Isaac Newton and Robert Hooke. He's also credited as being one of the first true chemists. Robert Boyle discovered that as you squeeze a gas into a smaller space, the pressure of the gas increases. Much like a spring, when you push on a spring, it pushes back. The opposite is also true. As you expand the volume of the container holding a gas, the gas's pressure will decrease. For Boyle's law to apply, the temperature and the amount or the number of moles of the gas must be held constant. Here's an animation that demonstrates Boyle's law. The gas is held in an airtight container as a piston moves up and down. The molecules of gas are represented by these black dots. You can see as the piston moves, the amount of gas is held constant. The temperature also remains constant. As the piston moves downward, the volume decreases. As the volume decreases, the pressure increases. The graph to the right shows this relationship. As the volume goes down, the pressure goes up. According to Boyle's law, volume and pressure are inversely proportional. This means as one variable goes up, the other variable goes down. This is the symbol for proportional. So this equation means that volume and pressure are proportional. Notice that pressure is in the denominator of this fraction, 1 over p. When you put a variable in a fraction like this means that pressure is inversely proportional to volume. Boyle's law explains why we should never hold our breath when scuba diving. Pressure changes very quickly when diving below water. For every 10 meters of depth, the pressure increases by 1 atm. That's 1 full atmosphere of pressure. When you're at a depth of 10 meters, you're experiencing 2 atms of pressure. When at a depth of 20 meters, you're experiencing 3 atms of pressure. Pressure regulators used in scuba diving deliver air at a pressure that matches the external environment. So when you dive to 20 meters of depth, you are breathing in air at 3 atms of pressure. If you were to swim to the surface from this depth, while holding your breath, the air would expand in your lungs. Due to the decrease in pressure, the volume of air would increase. The tissues in your lungs are delicate and would rupture. So one of the most important rules of diving is to never hold your breath. Volume is inversely proportional to pressure. Because units of volume and units of pressure have different increments, we have to apply a constant. If we use the correct constant for the units being used, volume is exactly equal to a constant divided by the pressure. If you multiply by pressure on both sides of the equation, pressure times volume is equal to this constant. In other words, pressure multiplied by volume is constant, so for any two sets of conditions, the pressure times the initial volume is equal to the same constant as a second pressure and volume. We can ignore the constant, and thus Boyle's law can be stated as follows. The initial pressure multiplied by the initial volume is equal to the final pressure multiplied by the final volume, or P1 times V1 equals P2 times V2. This is the form of Boyle's law that you should know and remember. Now let's do an example using Boyle's law. Our problem is to calculate the pressure of a gas that is initially at a pressure of 765 millimeters of mercury and at a volume of 1.78 liters. This gas is compressed to a volume of 1.25 liters. Let's identify our known variables. P1 is equal to 765 millimeters of mercury, V1 is equal to 1.78 liters, and V2 is equal to 1.25 liters. Recall that Boyle's law is P1 times V1 equals P2 times V2. So we need to calculate P2. So Boyle's law is P1 times V1 equals P2 times V2. In order to calculate the final pressure, we should isolate this variable. In order to do that, we need to get rid of volume on the right side of this equation. Currently, V2 is multiplied by P2. So if we divide this side of the equation by V2, that cancels V2. But whatever you do to the right side of the equation, you have to do to the left side. So we must divide by V2 on the left side as well. Let's rewrite that. P2 is equal to P1 times V1 divided by V2. Now we can substitute our variables for the numbers that are given. P2 is equal to 765 millimeters of mercury times 1.78 liters divided by 1.25 liters. Before we even do any calculations, we can check our work, and we see that liters cancel. Whenever you divide one unit by the same unit, that unit cancels. So liters cancel out, and we're left with millimeters of mercury, which is a measurement of pressure. We're trying to calculate pressure, so that's good. That's what we want. Okay, so let's do our calculation. So in your calculator, you want to type 765 times 1.78, and you want to divide that by 1.25. Your raw answer should be something like 1089.36 millimeters of mercury. But we need to round our answer to the proper number of significant figures. This problem is all multiplication and division, so that's the rule that will apply. And if we look at our given values, they all have 3 significant figures. So, our answer should be rounded to 3 significant figures. So this 8 is going to be our 3rd significant figure. So we probably should write our answer in scientific notation. The 8 will be rounded up because it's followed by a 9, which is 5 or greater. So the 8 should be rounded up to a 9. In scientific notation, our answer would be 1.09 times 10 to the 3rd millimeters of mercury. And that is our final answer. Let's try another example using Boyle's law. A cylinder with a piston has a pressure of 4 atms and a volume of 6 liters. What is the volume of the cylinder if the pressure is decreased to 1 atm? Let's identify our given variables. P1 is equal to 4.0 atms, V1 is equal to 6.0 liters, and P2 is equal to 1.0 atms. Recall, Boyle's law is P1 times V1 equals P2 times V2. So the variable we need to identify is V2. Okay, let's rewrite our equation. P1 times V1 equals P2 times V2. We need to isolate V2. We do that by dividing both sides of the equation by P2. Remember, that makes P2 cancel on the right side of the equation. And now we're just left with V2. Rewritten, V2 equals P1 times V1 divided by P2. And let's substitute our given values. V2 is equal to 4.0 atms times 6.0 liters, all divided by 1.0 atms. Units of atms cancels, we're left with units of liters, and since we're calculating volume, that's a good sign. Put this in your calculator, or perhaps you can do this mentally, and you'll get V2 is equal to 24 liters. Remember, all of our given values only have 2 significant figures. Our answer must reflect this, and so we only have 2 significant figures in 24 liters. One last thing I wanted to mention about these types of problems is it's important to check your work. In this problem, our answer was that V2 equals 24 liters. Remember, Boyle's law says that if the pressure increases, the volume should decrease, or if the pressure decreases, the volume should increase. In this problem, the pressure went from 4 atms to 1 atm. The pressure decreased So according to Boyle's law, our volume should increase. If we look at the volume, it went from 6, our answer is 24, the volume increased, and it appears to be in a reasonable amount. We have the correct units, and so we probably have the correct answer. That's the end of part 1 for chapter 13, the gases. Stay tuned for part 2.